Hey everyone, today we're looking at the paper Multiscale Transformer Language Models by a bunch of authors from Facebook AI Research. So, language models typically operate on a fixed scale, like on the word or the subword level. They take chunks of text, let's say 512 tokens, and they try to predict the next word that is most likely to follow this chunk of text. However, it might be beneficial to have models that operate on multiple scales, not only on the word level, but on a kind of more abstract, high-level scale, which would allow to better capture long-term dependencies, potentially filtering out also some of the local noise. And also it might lead to more memory efficient models, which is the main focus of the authors of this paper, where they propose a bunch of new language model architectures which operate on multiple scales rather than the fixed scale of the base transformer language models like the GPT-2 or others related. And their models can go up to 30 layers, however, have up to 23% smaller memory footprints and achieve better perplexity compared to vanilla transformer models, which have less number of layers. And so let's go into the details a little bit then. So the authors in particular propose two kind of big architectures that take a different approach to do this multi-scale language modeling. We have first a top-down model which starts from coarser representations, let's say from segments of multiple words of the input text, and then actually does some upscaling. I'll talk about that in a second, but then you also have a bottom-up model which starts from the high level, from the granular representations of individual words, and then goes into lower level. So first of all, the top-down model, so what they're doing is they are taking windows of words, let's say 16 words, as shown in this example here. So you have your words from x1 to x16, then from x17 to x32, and so on and so forth until 512, let's say, if your context size is 512. You're applying some average pooling in this case, and then you actually have some transformer layers, and then you have some convolutional upsamplers, which are actually trying to restore back the resolution into, let's say, 512 again, resulting in a more granular final representation. And then you are trying to make the prediction for the next most likely token in your sequence. So because of this coarse to granular approach of this model, this is the top-down model. You also have the bottom-up model, bottom-up multi-scale model, which starts with the granular representations of words or subwords here, and then you apply some pooling or convolutional layers. It seems that average pooling works the best in this paper. So you pool to produce more and more coarser representations, which are more high level. For example, let's say you go here, and then you have some transformer layers and some other layers which are further processing this, and then you make the final prediction for your final for the next word that you're trying to predict. So this is how these two models work, and intuitively, well, yeah, they might be achieving different objectives. They might work a little bit differently. But the goal is to try to, like, for example, here you are doing processing on these layers here, for example, will be not doing as much computation and will be more memory efficient potentially as well, because they're operating on much shorter sequences. And similar for these layers here, causal transformer layers, 16x hierarchy, whatever. Those will be potentially more efficient, leading to some more efficient final models. And then a final kind of new thing proposed in this paper is a special retina attention mask, which they're not always using in all of these models, but the idea of this retina mask is to kind of force the attention of these models to always focus on nearby words. For example, let's say this is an attention mask we're looking at the highest granularity, and the attention, it might be beneficial to focus the attention on words to always go to nearby word locations. Let's say you have a preference, you always want your attention to be focusing on words with distance 50, let's say. So only words in location less than 50 or more than 50 at your current token that you're computing your attention for. And this is done by this retina attention mask. So it allows you to limit the attention kind of width of your models, which might be beneficial because it might make the models more focused on the local contexts. So I hope this gives you some overview of these different architectures. So now let's look at some results of these different multiscale language models. This figure somehow seems to be the most important, where we are comparing the test perplexity of different models of different sizes of memory footprints measured in gigabytes stored in disk. We have a lot of different models from 10 gigabytes to 24 gigabytes, and we have three architectures. We have the vanilla transformer model with different number of layers from 5 to 14. This is a GPT-2-like model as far as I'm aware. And then we have our top-down and bottom-up transformer models with different architecture variants and different memory footprints. But basically the bottom line, first of all, it seems that the multiscale models seem to offer some benefits in terms of they're more memory efficient than the vanilla transformer model in blue here consistently. They're able to give you a better perplexity versus memory trade-off. So if you're short on memory, you might as well use these multiscale architectures. And also it seems that the top-down transformer architecture is performing a little bit better given a memory constraint here. So the authors do a lot of different other ablation analysis to try to figure out which particular architecture feature is beneficial. There's actually a lot of details here. I will not go into those. I would encourage you to read those. But there's also some interesting analysis of the retina attention. I actually found this discussion about the retina to be not very detailed. Like, I'm not sure actually when the retina attention is used and in which models. But it seems that they do claim that using the retina configuration seems to be beneficial over the vanilla model, at least. That is basically this table column here is the attention context window, and you can see that in the default case you have a context window of from 0 to 512, which is the context size. With the Retina, you can apply more adaptively different context sizes. Also, depending on where you're at and which model you're using, because if you're using the multiscale model, maybe for maybe in your layer you're gonna have different context sizes. But it seems that the Retina attention model might also provide some benefit over the vanilla model. But this, I'm not 100% sure about this. You have to read more about that in the paper. So this is the basic overview of this paper. In overall, the authors propose a few novel architectures which seem to be more memory efficient than using a vanilla type of language model, which operates on doesn't have processing layers in particular scales, and yeah, this leads to more memory efficient language models. So that is all that I wanted to cover for today. Thanks for watching, and please like and subscribe for some more upcoming NLP videos.